Stereochemistry. In this chapter, we will study about stereochemistry, that is, the relative spatial arrangements of atoms in 3 dimensions. We will learn about chiral molecules and properties of chiral molecules like optical activity. We will learn to name the chiral molecules based on their absolute configuration using the CAHN-INGOLD-PRELOG rules. We will learn to draw the perspective and Fisher projections of chiral molecules. We will learn about diastereoisomerism in molecules having more than one asymmetric center. Stereochemistry. Compounds that have the same molecular formula but do not have identical structures are called isomers. Isomers can be classified either as constitutional isomers or stereoisomers. Stereoisomers can be further classified as either cis-trans isomers or isomers that have enantiomeric or diastereoisomeric relationship. In this section, we will be dealing with stereoisomers that have enantiomeric or diastereoisomeric relationship. Enantiomers of alanine, an essential amino acid. Alanine, an amino acid, can exist in 2 stereoisomeric forms, 1 and 2. They have the same constitution and bond connectivity, but permanently differ in the spatial arrangements of the groups that are attached to this central carbon. 1 and 2 have the relationship of an object and its non-superimposable mirror image. Stereoisomers that are related as object and its non-superimposable mirror image are called enantiomers. The central carbon, to which 4 different groups are attached, is called an asymmetric center or a chiral center or a chiral carbon. 1 and 2 are the 2 enantiomers of alanine. They are non-superimposable mirror images of each other. Chiral and achiral molecules. While chiral molecules have an asymmetric center, achiral molecules are characterized by the presence of symmetry in the molecule. For example, glycine, an amino acid, has a plane of symmetry and hence is achiral. Molecules that have a center of symmetry are also achiral. Achiral molecules are superimposable on its mirror image. Optical activity. Optical activity is the ability of a chiral molecule to rotate the plane of plane polarized light consisting of a single wavelength and is measured using a polarimeter. In a typical polarimeter, sodium lamp gives out a single wavelength at 589 nanometers. This light is not plane polarized. That is, the plane of its electrical vector can have any direction along the line of travel. When passed through a polarizing filter, all the waves except those that have their electrical field in the same plane gets filtered, resulting in plane polarized light. The plane polarized light is then passed through a sample tube containing the chiral molecule. The sample is optically active if it rotates the plane of the plane polarized light. The direction and magnitude of rotation are measured using a second polarizing filter called the analyzer and is cited as the observed rotation alpha in degrees. Specific rotation. The two pure enantiomers of a chiral molecule exhibit the same degree of rotation but in opposite directions. Rotation of the plane polarized light in the clockwise sense is taken as positive or dextrorotatory, and rotation in the anti-clockwise sense is taken as negative or levorotatory. If the two enantiomers of a chiral molecule are present in equal amounts in the sample tube, there will be no net rotation. In other words, the mixture will be optically inactive. All achiral substances will also be optically inactive. Specific rotation. The observed rotation of an optically pure substance, that is to say containing only one enantiomer, depends on how many molecules are in the path of the light. Since concentration has an effect on observed rotation, alpha, chemists use specific rotation to express the optical rotation of a substance. Specific rotation can be calculated by taking into account the length L of the sample tube in decimeters and the concentration of the sample C gram per milliliter, the temperature in Celsius and the wavelength of the light are also cited. If a substance contains unequal amount of two enantiomers, then the enantiomeric excess of the enantiomer that is present in excess can be calculated. For this, we must know the observed rotation of the substance and the specific rotation of the enantiomer that is present in excess. Enantiomeric excess is equal to observed specific rotation divided by the specific rotation of the pure enantiomer multiplied by 100%. Absolute configuration of a chiral molecule with one asymmetric center. The spatial arrangements of atoms around the steric center is its absolute configuration. The direction of rotation nor its magnitude can reveal the absolute configuration. Chemists use the letters R and S to designate the absolute configuration of the two possible enantiomers of a molecule like alanine containing one asymmetric center. In this system of nomenclature, the substituents on the central carbon are ranked using the CAHN-INGOLD-PRELOG sequence rule, and then the configuration is assigned as either R or S. The two enantiomers of alanine 1 and 2 can be assigned absolute configurations as per the following rules. 1. Rank the substituents at the steric center as per the CAHN-INGOLD-PRELOG rules. NH2 gets the highest ranking, followed by the carboxyl group, followed by the methyl group and hydrogen. Orient the molecule so that the lowest ranked substituent, that is hydrogen, points away from you. You now see the three highest ranked substituents in front of you. Draw an arrow from the highest priority to the second highest priority group. If the arrow appears clockwise, it has an OR configuration. If the arrow appears anti-clockwise, it has an S configuration. Hence, 1 has S and 2 has OR configuration. Drawing perspective formula of a chiral molecule. The structure of the amino acid serine is given here. Draw the perspective formula for its S enantiomer. Step 1. Identify the central chiral carbon and draw the bonds A and B on the central carbon. The bonds A and B, by convention, are adjacent bonds and lie on the plane of the paper. Draw the hatched wedge bond C, which represents a bond away from the plane of the paper to the back. Draw the solid wedge bond D, which indicates a bond coming towards you from the plane of the paper. Connect the group with the lowest priority, hydrogen, to the hatched wedge bond C. Connect the group with the highest priority, NH2, to the bond B. Draw an arrow counterclockwise from the group with the highest priority to bond A. Attach the next highest priority group, carboxyl, to bond A. Attach the third highest ranked substituent CH2OH on bond D. Fisher projections of stereochemistry. Fisher projections are representations of the absolute configuration of a three-dimensional chiral molecule in a flat two-dimensional drawing. In Fisher projection, the four bonds around the asymmetric center is divided into a pair of vertical and horizontal bonds. The vertical bonds point away from you and the horizontal bonds point towards you. To draw the S enantiomer of alanine in Fisher projection, put the lowest priority group on one of the vertical bonds and the highest priority group on the other vertical bond. Put the groups ranked 2 and 3 in two horizontal bonds in such a manner that when an arrow is drawn from the highest ranked group to the next highest ranked group, it is in anticlockwise direction. To draw the OR enantiomer of alanine in Fisher projection, put the lowest priority group on one of the vertical bonds and the highest priority group on the other vertical bond. Put the groups ranked 2 and 3 in two horizontal bonds in such a manner that when an arrow is drawn from the highest to the next highest group, it is in clockwise direction. Fisher projections of stereochemistry. Note, a 180 degrees rotation of a Fisher projection results in no change in the configuration at the chiral center. However, a 90 degree rotation of a Fisher projection results in the inversion of configuration at the chiral center. Assign the configuration of the following Fisher projection formula A. Arrow from the highest priority to the next highest priority group point anticlockwise direction, indicating it to be S configuration. However, the lowest priority group is in an horizontal bond. Hence, the absolute configuration of this structure will be the opposite of S, that is R configuration.